Hey everyone. This week we continue our discussion, our seminar series on categorical structures in quantum mechanics and the speaker will be Redi Haderi, speaking about symmetric monoidal categories and additional structure needed for categorical quantum mechanics. Ready?
Yes, ready. Okay, so today, uh, so I guess this is monoidal categories, talk number 2. Okay, and the way I'm really thinking about this sequence on monoidal structures is really stuff we can do / model with monoidal categories. Okay, uh, so I'm looking at it like from this sort of angle because this is like our objective is to say something about quantum theory using the formalism that monoidal categories have to offer. Okay, so Walker already introduced us to monoidal categories last time, also to also to model categories in another seminar. So monoidal categories, I mean, pretty much it's a category C. So just to sort of refresh our memories, we have a monoidal product. So this is monoidal product. And this is the unit. That's how we denote it usually. And some other stuff, associators, unitary isomorphisms, etc., which you can find in Walker's notes. And the formalism we are interested somehow is this string diagrammatic notation. So if I have objects A and B and C, we can form, A tensor B, which is still an object in C. This satisfies many, many properties. And the way we represent it is just saying, here is A, here is B. And by sort of putting them next to each other, we signify that we are doing the product. Okay, and then for morphisms, etc., which will come up during this talk as well, you can refer back. So I think so I'm not sure where to trace back the idea that monoidal categories have a place in physics specifically or applied mathematics in general, but I think one of the driving forces behind thinking of using the language of monoidal categories is this picture, in the sense that we have things in parallel, and using this sort of product, we can model having things in parallel and doing operations with them. Okay, so we have, so I'm not going to do a full rediscussion of monoidal structures, just this is a remark. Okay, so Walker already talked about symmetries, for instance. He already talked about dual objects. Okay, so and we'll proceed with concepts which are of interest for our purposes. Okay, so, and here I will continue keeping in mind the examples of the category of sets with the Cartesian product and the set with one element as the unit, and the category rel. So these are sets with relations, again Cartesian product, again one element set as unit, and of course our category of interest is finite dimensional Hilbert spaces with linear maps. And here we have tensor product over the complex numbers, and the field C itself serves as a monoidal unit. Okay, so these, I'm going to run most of the stuff I do today through these examples. And I suggest sort of, if you're trying to grasp the material, just find an angle through one of these examples to understand the concept. Okay, or another example that it's easier for you, etc., and develop an angle. Okay, that's what I'm trying to do myself. Okay, so notion number one I want to discuss today is that of a scalar. So Abramsky-Koche say miracle of scalars. So I'm just going to put it here. Miracle of scalars. So what sort of miraculous thing is going on? Well, so let's put this as a definition actually. So let C tensor I. There is extra data which I'm not writing, okay? Associators, etc. So this is abbreviated notation technically. So be a monoidal category. So a scalar is a morphism from I. So let's say S. S is a scalar. Of course, so in examples, I want to start with the third example because it makes much more sense there. Okay, so the monoidal unit is just the vector space C. Okay, so in finite Hilbert spaces, so the scalar, according to this definition, is a linear map C to C. And when I say linear, I mean actually linear with respect to complex numbers, of course, because that's our base. And now this is just the complex numbers, and this is just the complex numbers. Everything is determined where you map the element 1 here. So 1, pick any element here, say S, uniquely determines such a linear map. Okay, so indeed, I mean, we have actually a bijection between homomorphisms in F Hilb from C and complex numbers itself. So yeah, you pick the S here, take the map which sends 1 to S, and vice versa. Okay, so the notion of scalar is sort of abstracted, I wouldn't say from here, but from the general idea of vector spaces. Yeah, so in other examples, for instance, it could be less meaningful. So let's say example number 1. So let's take sets. So in set, a scalar would be what? The function from the 1-point set to the 1-point set. And of course, what could this function be? There's unique such a function, right? You have no choice. So there's a unique scalar in this language. Not very illuminating example, okay? So this is the unique scalar. Yeah. Okay. So in example number 3, we do get interesting stuff. So in rel, so what could be a relation R from the 1-point set to the 1-point set? Okay. So we have two options. So let's just depict them. So I have my element here, my unique element, and my unique element here. So of course, one possible relation is nothing, right? So let me call that false, like there is nothing here. And the other option is to have this pair of elements in the relation. So let's call this true. Yeah, so this is interesting. Now we have two types, two scalars, true and false. Okay. So about this, I'll say something general about it. So general fact. The scalars say, which are things like this, can be multiplied by composition. So if I have a scalar S and I have a scalar T, here is T composed with S. And so the general fact is that this multiplication is commutative. Which means ST is equal to TS for all. So I would very much love to prove this fact, because it's this is like the favorite type of argument for an algebraic topologist. Okay, so we can discuss afterwards. This is called the Ekman-Hilton argument. Okay, it's the same, for the same reason second homotopy group is abelian. This is commutative, etc., etc. Okay, but I'm just going to leave it stated as a general fact, which holds true in any monoidal category. So in the examples, I mean, here we can see clearly, because I mean, multiplication of scalars is just multiplication in C. So of course it's commutative, right? So you can swap factors. And the interesting part is to see now in example number 3, how does multiplication look like? Okay, so let's continue with example 3 and work out how do we do this. So let's do it with a table. So what happens if I compose false and false? Well, we can understand it with a picture. So I have nothing and I compose with nothing. Of course I get nothing, so it's false. And so what happens if I compose true and false? So I have true composed with false. Of course, you get nothing here, right? Because you have no link. So this remains false. And what happens if I compose false and true? So true composed with false, again, here, and there's nothing. So this remains false. And when I do, of course, true composed with true, true. So this is really the conjunction. Okay. So one way to put this in more algebraic language is to say that the commutative monoid of scalars in the monoidal category rel is Boolean values with conjunction. Okay, if we want to make like a fancier statement, then it's So this is what we have in general. Now, how do we present like a little graphical note here? So in terms of what we have been developing so far, how would we depict in string diagrammatic terms a scalar which is a morphism I to I? Okay. So remember that if I have a morphism A to B, the way we depict this is here you have A, have F, and here you have B. And if one of these is I, we just don't write anything, right? So a scalar is really funny. Like, it's going to be depicted as just this. Just the operation. There is no input and no output. Okay? And how do we tensor? Well, we can do things like scalar multiplication, for instance. So scalar multiplication. So let's say I have F from A to B, have S here. Okay, so this sort of signifies multiplying, well, it's the tensor product, but it's sort of scalar multiplication. Okay, so let's write with the tensor notation because it's better. And here I have A and nothing, so this is still A, and this is still B. So we see this very sort of intuitive idea of scalar multiplication. Okay, if we write it in sort of more classical diagrammatic way, do I want to do it even? Okay, so we have F from A to B. So what we do is that we form we do A tensor I, B tensor I, and we do F, well, I guess, oh, wrong. So I have I tensor A and I tensor B, and this is just S tensor F. But now this is a map from I tensor A to I tensor B. And so I apply the structure isomorphisms on A and B. And what I obtain going this way is, so I'm abusing notation, sorry. So I apologize. So let's denote this by the dot, because the tensor is really has source I tensor A and target I tensor B, right? By the rules. So the scalar multiplication is from A to B. I mean, morally these are the same thing because these things are isomorphic, but to be like 100% precise. So we have this sort of thing. Or you just do this. Okay? So, good. Any questions so far? Okay. So now we come to a more, I would say, the most interesting concept for today. So that of a dagger category. So the way I'm ordering the subjects from scalars to dagger category, so they are independent, okay? But they sort of come together in the end, so I have to pick an order. Unfortunately, time is linear. So let me quickly do the definition and then sort of see what happens in examples. All right, so definition. Let's see, be a category. No assumption of being monoidal. So, right, just a category. So a dagger structure on C consists of an identity on objects contravariant functor which we write as dagger, and thus the name of the structure is just by notation, which is very silly. So the functor is contravariant. I'm going to write it C to C op, or you can write C op to C, but I think this is better. Okay. Yeah.
Consists of an identity on objects and a contravariant function. How am I supposed to? I don't.
So
put hyphens between identity on objects and a comma after objects, and then it's two adjectives modifying functor.
Okay.
yeah, it's like a
From a contravariant function.
yeah,
Okay.
it's like saying you have a fine-tuned free whatever, like it's a bunch of adjectives. So this is a separate thing, and this is a yeah. I'll say what it is. So yeah, comma.
Okay.
Okay, let me
Thank you.
box these. So this is one property of this functor.
I know it seems silly. But
No, it's not silly. In language is important. So this is one property this functor satisfies, and this is the other feature. So there are two features. Okay? So it's identity on objects and contravariant. Right. So let me write the functor. Let me write it here, because I'm going to say what it does. So we have this dagger functor, C to C op. So C op is just obtained by reversing the arrows, okay? Now, these two categories have the same objects. So what identity on objects mean is just that if you have an object what this functor does is nothing. You just go to the same object. Okay? Now the contravariant part comes in the morphisms. Okay? So what if I have a morphism A to B being contravariant, so I apply the dagger functor. Now this gives me a morphism from A to B in the opposite category, which is to say a morphism B to A in the category C. Okay, so, and we write F dagger for this. Okay, so F dagger is a morphism B to A in C. So this is equivalent with saying that F dagger is a morphism A to B in C up. Same thing, just language. Okay, so to each morphism A to B, we assign this morphism B to A in C, and that's what the dagger function does. Such that, number one, so let me make sure I'm consistent. Okay, so this should respect compositions. So G tensor F dagger is F dagger composition G dagger. And I mean, what am I saying? So if I have two composable morphisms, F and G, form their composite, G composed with F, and now I apply the dagger functor. Okay. So the objects still are the same. Here I have F dagger, and here I have G dagger. I can form the composite G dagger, F dagger. So this composes with this. And this has to be the same as applying dagger to the composite. So this is part of being a functor.
So then, but F dagger is morphism from B to A to C up.
Yes, no. So it's a morphism from B to A in C. Maybe this, I shouldn't have written it here under C up. I put a line here,
Yes.
which is the same as a morphism from A to B in C up. Okay, that's why I sort of emphasize this. Okay? Yeah, this stuff can be confused at first. So just this is just the structure for any morphism A to B. I give you a morphism B to A, and it has to satisfy some properties. So don't worry about the technical language of things. So property number 2 is that if I have the identity morphism and I do dagger, is again the identity. So these two are really the axioms of being a functor. Okay, so far, these are just functor assumptions. Actually, just by saying that we have this functor, I have said 1 and 2, really, right? This says it preserves composition. This says it preserves identities. So really, so the number 3 is the kind of not deriving from functoriality, is that I do dagger, dagger, get back the same morphism. Okay, so that's your definition of dagger category. And the examples are
So C up has also a dagger expression.
C op has also a dagger structure. Yes. Yeah, that's an interesting. Yeah, okay. So let's actually write it. So fact C has dagger structure implies C op has dagger structure. Good. Yeah, just by going back. Okay, so the first example I want to look at is actually functions and relations, because I think it's like the paradigmatic example. So this is example now number 1 of dagger category. So in sets with relations as morphisms, so let's say I give you a relation R, A to B. A and B are sets, and this is a relation. Okay, so this is just a subset of A cross B, if you want. Okay, or if you want to draw a picture, here's your set A, here's your set B, and let's say we have something like this. Whatever. So the arrow indicates that the pair is part of the relation here. So you can draw pictures like this. And if you want to understand composition, actually I was doing it earlier, you can draw these pictures. Okay, your choice, okay? Do this however you want. If you want matrix multiplication, go. Okay, choose your favorite angle. This is mine. Now, what could be, so if I tell you, okay, so off the bat, if I tell you I'm giving you a relation R from A to B, how could you possibly give me a relation from B to A?
Just reverse the arrow.
Sure. Okay, and that's your dagger. Okay, so the dagger is just, I think of this being in this direction. Okay, here you go. So it's really like the prototypical example where this happens is this. Okay, formally we could say, so now I need to define our dagger as a subset of B cross A. So if you're doing your abstract math exam, you get 0 points for drawing this picture. You have to write things properly, unfortunately. So we say that BA is in our dagger if and only if AB was originally in R. Okay, and this is how you define the dagger. Now, those properties can be seen by eye, right? So this being functorial, etc., I suggest you check it. You can think in terms of these pictures. But really, this third property here, that when we do the dagger and dagger again, what we are really doing is reversing the arrows and reversing them again. So we get the same thing back. Okay. Now, what happens in the category of sets? Could we have a dagger structure? Right? So I give you sets A and B. So if I give you a function, now functions have to assign a unique element in the codomain to elements in the domain. So you cannot have these sort of multiple arrows coming out, right? So now it's sort of, there is no obvious way to go from B to A, which we can derive given a function f, okay? So no dagger structure on set. Now how can we prove there is no dagger structure on set? Well, it's an easy exercise, and since it's easy, I will do it, okay? If it's difficult, I will leave it as an easy exercise. So that's what mathematicians do, except us, of course. So okay, we can prove a little a little fact. So this is again general fact about dagger categories. So C has a dagger structure, implies for all objects A, B, let me be up rigorous. The set of morphisms in C from A to B is in bijection with morphisms in C from B to A. So there is a bijection. This is really just evident since we have this. So because, I mean, what do? You go from here to here with a function, with the dagger function, right? And then you go from here to here with the dagger function. And now dagger and dagger gives you identity. So this is a bijection. Okay, so, but for sets A and B, these two sets are not the same. Okay, so this fact implies that we cannot have a dagger structure in the category of sets. And you can easily find two sets, and these two sets will be different. Okay, any questions? And so in our third example, and I guess, well, I'm not sure, but perhaps this is where the dagger notation and the notion of dagger category comes about. So for finite Hilbert spaces, so if I have a morphism h to k of Hilbert spaces, I define f dagger from k to h. So I guess Salman already mentioned this. So in terms of matrices, okay, so if I have a matrix, we use f dagger to mean that we do transpose and then conjugate. Okay. If you don't want to pick a basis, etc., you can say this f dagger. So this is the unique morphism or linear map such that so on the inner product it has this property. Let me check that I have the directions good. Okay, so what is it now? FAB is equal to A F dagger B. So now A needs to be in H, B needs to be in K, and this is inner product in K, and this is inner product in H. So you can think of it. So I think they call this adjoint, isn't it? Yeah. So this is called the adjoint of F. Yeah. So if we were going to go really into category theory, from this we can see some sort of adjoint functor stuff, but that's another story. Okay, and this has the dagger structure. I mean, you can verify it as an exercise that if you do double dagger, really from this, it's pretty clear, right? You transpose conjugate, and then you transpose again and conjugate again, you get the same thing. Right, so yeah, this is the story really of dagger structures. Now, there are things we can do with this. Let me make sure I didn't forget anything. Okay, so good. Do you have any questions while I have a sip of water? Okay, from what I've gathered and from the REL example, so I think this is an interesting sort of concept, even from the pure math side of things, of course. I would sort of state a personal opinion. So a dagger structure, okay? So dagger structure is really a form of non-deterministic structure, if we want to use terms which are closer to quantum theory. Okay, because look at the difference between functions and relations, right? So function is something pretty deterministic in nature. Takes elements to elements, there is no other thing you can do, but here you can like span out. It's not deterministic, so you have this reversing operation. Okay. Now, there could be an angle to see that way, so we can come back to this point in the future, perhaps. But really, that's my 2 cents. Okay, so let's say a couple of other things. Okay, so how should I frame this? Okay, let's say dagger structure versus inner product. Okay, so in some sense, the dagger structure really allows us to recover inner product in Hilbert spaces. Okay, and how do we do that? So again, going back to something that Salman has explained to us in his lecture, this idea we want to formulate. So let okay, sorry, I need another definition before going. So this, okay, let's save it for later. Okay, because I haven't prepared all the definitions yet. Okay, so now we can extend ideas from the usual things we have in Hilbert spaces to general monoidal categories with dagger structure. Let me put this like this. I haven't defined yet what this is, but let me try. So, okay, so example. So let's say the stuff I need. For instance, okay, so let's see be a dagger category. So of course, by dagger category, I mean a category equipped with functor like in the definition I just put. Okay. So, so a morphism say f a to b is said to be like we can adopt this term, say self-adjoint, if, well, f is equal to f dagger. So I guess it's implicitly assumed here that f is from A to A. Okay, this only makes sense. Okay, let me maybe make a note here. This only makes sense if f is really from A to A. So foundations of math are really boring, but we have to respect them. We don't actually, but that's another topic. Okay. So, and we call it self-adjointness here, and unitary if, so let's put it like this. The dagger is actually the inverse. So I have A to B, F. If I compose with the dagger, I get identity A and B to A. So I do this composition and I get identity on B. Unitary. So this is from Vickery-Hoynen, but I think also Koch-Abramsky. I think there is an extra condition. I don't remember. There might be an extra condition for it to go. They do define what is an isometry, but it's, yeah. So these triangles commute. So I think, I mean, you can go on with the list, okay? So any term that you can apply, say, to matrices, for example, you call this the adjoint, right? The dagger. And you say a matrix is self-adjoint in ordinary parlance with Hilbert spaces. So now I will say a morphism is self-adjoint if it satisfies this, right? And I will say a morphism is unitary if it satisfies this. So in particular, it means it's an isomorphism, okay? So let's put a little note here. So unitary, so F unitary implies F is an isomorphism. For obvious reasons. Okay. Right. So now there is a actual other definition. Okay, so where we wanted to go is a monoidal category with dagger structure. We have the monoidal structure and the dagger structure, and we want them to interplay well with each other. Okay, so the definition is the sort of obvious thing you can write at this point. So I'm not going to contemplate much on it. So let this be a monoidal category. Such that C has a dagger structure. Say dagger. So we say C is a monoidal dagger category if for all Fg morphisms in C, the dagger operation respects the tensoring. So F tensor G dagger is the same as F dagger tensor G dagger, and associators and uniters. So these are the structure morphisms that Walker explained in detail last time. So these were, so in the general definition of monoidal category, these were required to be isomorphisms. For example, we have A tensor I, say isomorphism into A. Okay, we require this to be an isomorphism. Now, with the dagger structure, I will require these to be unitary. Unitary implies isomorphism, so this is extra structure. Okay, are unitary. Good. Okay, so we can do more. So we can say braided, and I guess symmetric. Walker, did you use the term braided?
No.
No. Okay, symmetric.
I use the term braiding for the
Okay, so I will say, we say this is symmetric if the braiding maps, braiding isomorphisms are unitary. Cool. Okay, so so okay, this is the actual structure that we want. Okay, so, and examples are really Rel and Hilb are examples of this. So just, I guess, you need to sit down and actually see that these axioms are satisfied. It's not difficult, it's just routine check. Means the monoidal structure interplays well with the dagger structure. That's it. Right. Okay, so how are we on time?
You have half an
Good. Okay, fine. So let me just put it here. Examples. Rel and Hilb of monoidal dagger structures. Okay, so let me go back to the thing I was trying to say, thinking we know this. Okay, so dagger versus inner. So one interesting. So one statement Vikari Hoinen make in the book is that, like in the very F here. So in the category of finite Hilbert spaces, we define morphisms to be all linear maps. Okay. They don't have to preserve norm or any other condition on the norm. It's just linear maps. So the inner product is not really important in the morphisms. So the thing we know is that the notion of morphism dictates the behavior of a category. Okay. So this is sort of, I want to make the point that the inner product is recoverable from the dagger structure in a way which people who have worked with Hilbert spaces can possibly guess. Okay, so in general, let's see answer I, and let me add the dagger here, be a monoidal dagger category, right? So if I have a morphism from the unit to some object, let's call this A. So graphically, I'm going to draw it. So, or one way to think about this graphically is as a cat. So, sorry. So this is A, and this is A. So this is called the cat associated well, just let's say a cat, sorry. And we can depict it like this, okay? And the bra is, well, so let's say B. So just like Salman was explaining to us in his lecture, we can think this is an operation, well, from A to I, and I is like empty space, right? So we can define sort of a bracket we want to. So I have AB And this composition sort of makes sense. Okay. So this becomes bracket. Right. So now thing is here now, if H is a Hilbert space, I is the complex numbers, so a map C to H, as we discussed with the scalars, is determined by where 1 goes. So this goes to some element, shouldn't say I should say really some phi, I guess. And we write it as with this type of notation. And now it is easy to check, okay? So let me write it as a little fact here. So the actual dagger of this is just like the bra of it. Okay, so what is this? So this is now H to C, and what do I do here? I send, well, whatever. Let me say just A or B inner product of phi B, and this is, I'm sorry if I'm messing notation. You can tell how expert I am on this by these manipulations I make. So anyway, so the whole point is, like, if we knew the sort of from the dagger structure, just by knowing that we have this dagger operation, we know that for any element in H, there is this special element here, which is the dagger, and sort of composing in the category of finite Hilbert spaces, we recover the inner product, which is the bracket. Okay, so it's sort of, the dagger structure is trying to really behind the scenes play the role of the inner product, we could say, or one of the things it's trying to do is that. Okay. Okay. So yeah, this you just check. There's nothing to do. It's just a matter of, I really find it nice as a person with background in category theory that we can actually do this. Okay, so that's the thing I really find nice, and it makes this stuff easier to digest for me personally. All right, so I think this is all I have to say about dagger structures. So do we have questions? Okay, so the remaining time is, I guess, part 3 of this talk. So we talked about scalars, dagger structures, monoidal dagger structures, which is really, let me say again, a way to encode all these manipulations we want to do so that we can do, say, stuff like this, okay? It's nothing more than that. It's like, okay, so I have space here. Okay, so part 3 of this talk, I want to talk about closed monoidal categories. So this is a general So this concept has nothing to do in particular with quantum theory, while these dagger structures do, right? This is a general thing that occurs in all over the place, and people have formulated the stuff I'm going to write now ages ago and proved everything which is relevant. I will just sort of tell you what it is in somewhat sketchy manner, okay? So here's the definition. Okay, so a monoidal category C tensor I is said to be closed if for all objects A, B, and C, there is an object which I will denote square bracket. Has nothing to do with inner products or anything, just a notation. So this is an object in C, and this is called internal Hom object. There is an object this called internal Hom objects satisfying or such that for all A, B, C triple of objects, there is a natural bijection Hom in C from A to the internal Hom BC. So these are two objects in C. It's isomorphic to Hom in C from A tensor B C. So let me just say some stuff about the structure. Maybe here. So let me say what the idea behind the definition is. So there are two elements of the definition, okay? The existence of these special objects called internal Homs and this bijection here. So let me very briefly say what they are supposed to signify. So if I write Hom C AB, what I mean is the set of morphisms from A to B in the category C, okay? And this is just a set, okay? So saying, so this is just a set or a collection of things. Now, saying that I have an internal hom AB, which is an object in the category C itself, really means all the time in practice mostly that this set has the extra structure of an object in C. Okay, so says really hom C AB has extra structure. And now, if I take this set plus this extra structure, it gives me the internal hom AB, which is an object in C. Okay, and does this happen? Of course, all the time. This happens in general in all sorts of categories. So let me say idea number 1 here. So examples. Example number 1 is silly because for sets, so if I have 2 sets A and B, what is the internal hom set? It's just the set of those. There's no so saying that the set of morphisms has the extra structure of a set, it's already a set. There is nothing to do. So this is just functions between A and B. So here it's not, and same for rel, because I mean, being an object in rel means being a set. You just take just that set. Okay. So in vector spaces, in particular, looking at our example of interest, I want to define like a vector space first, okay? What is the vector space of morphisms between H and K, basically? Okay, so looking at this sort of explanation here, you look at first the set of morphisms and see if there is extra structure so that the morphism set itself acquires the status of an object. Okay, now if I have like 2 linear maps, you can do like scalar multiplication and addition pointwise. Yeah, I guess you have seen how to do this. Okay, and so we can see this as a vector space. Okay, and moreover, you can do a norm. I mean, this takes some figuring out the norm, but it can be done. And so you can form a Hilbert space where the vectors in that Hilbert space are morphisms like this, or matrices, if you wish. Okay, and you can add, multiply with scalars, do all that stuff to morphisms. So this really captures one of like this point of being there, an internal hom. Now the second part is just saying that the internal hom is good with respect to the monoidal structure. Okay. It's also called, so let me rewrite this. So this is saying that home in C, A internal home BC. So these are not two objects in C, and I can talk about morphisms from one to the other, is the same as home in C from A tensor B to C. And so let's look at the set example from here. So in sets, what does this amount to? Okay, so let's just work it out for sets. So let's say I have a map from A to BC. And what was BC? Just the home set. So this is just a thing. So let's give it a name, I don't know, like phi. So let's say I have a function on the left-hand side. So what does this do? To each A, it gives me a function from B to C. That's what this is doing. So this can be transposed into something from A cross B to C. How? Like you take AB, and now you evaluate phi A at B. So, and you can reverse the process. So if I give you a function from A cross B to C, to each pair I assign an element. You can build a function to each element of A, you assign a function which assigns, work it out, okay? You can go back with this. So this is also called, in the particular case of sets, but in other settings as well, exponential law. And let me just briefly say why is it exponential. Another possible notation for sort of functions between A to B is to say B to the A. Okay. So if we use this exponential notation, what is this saying? This is saying that, so let's go from here, C to the A times B really is the same as C to the B to the A, which is the left-hand side. Okay, so there's this neat way of thinking of this as an exponential law.
But in this case, are you talking about sets? The notation just applies to.
You can use.
Home sets as the also being.
So this notation of the exponential is not just in set.
Yeah.
But doesn't the first one here, C to A tensor B, refers to the right-hand side of the top isomorphism?
Yes. Okay, so let me.
I'm thinking of it as like a bracket A tensor B to C, but it's not, right?
You actually get the junction of hum objects as well.
I was going to say that next, yeah.
Yeah, but the notation is a bit easier, right?
No, that can be made really explicit.
Yeah, actually, it's kind of the next thing I'm going to.
Okay, maybe I'm confused about the notation. Bracket A comma B is different than the home A comma B, right?
Yes,
but
yes.
You're noting them.
Yes, so let me say justification and write something here, because it's really the next thing I was going to say. So time?
You can 8 minutes.
Sorry?
8 minutes.
8 minutes. Okay. Okay. So I will just say facts about closed monoidal structures, which we haven't developed enough category theory to prove them, but I will just state them. We are happy to discuss. I mean, the proof techniques are interesting, part of pure category theory more. We are happy to discuss after, during the week, whatever. But the following is true. So C tensor I closed monoidal implies that this isomorphism can be promoted to really this. So the internal hom between A and BC is actually isomorphic now in the category C as an object to the internal hom between A tensor B and C. You can prove that in general. So it's enough to check that we have this bijection of sets, which is natural, and you can prove this. It just follows in general.
I have a follow-up question.
Yeah.
So you're justifying this bracket thing, right? The object structure is somehow induced on the hom.
Yeah.
So, but,
yeah.
You know, does it have to be in general?
Yeah, it does.
In relation to always have to in relation to the hom set, or can it be?
I mean,
any object that has nothing to do.
In general, it doesn't have to do anything with the hom set.
Okay. In that case, does the hom set iso still imply this?
Yes. Oh. This is in general. Like no further assumptions on this. In general, it just follows by Yoneda's lemma. So yeah. So using this, you can show that these two objects in C represent the same functor in the Yoneda embedding. And then these are isomorphic objects in C. If we can discuss the proof sometime, if anyone is curious.
You consider maps inside of that, and then
Yeah.
repeatedly apply tensor.
Yeah. So that's the technique.
Oh, okay.
Yeah.
Okay, interesting. Yeah.
Yeah. And
the examples I know usually have this. I mean, you just define the hom set and then put extra structure.
Exactly.
But is there any nice examples where they're not the same?
You could cook up something with posets maybe.
Okay, maybe they're not
where
so
they're not. I mean, the examples we have in mind are really vector spaces, abelian groups, sets itself.
Yeah, I mean,
which
in those cases, this is okay. I mean, you don't even need category.
Yeah.
Yeah, I was just curious in general.
There are such cases. Like I know that there are some kind of value enrichment.
Exactly. Posetal. Yeah. There, it doesn't really make sense to say extra structure on the set. Yeah. And in general, you can prove, for instance, that the internal hom from the unit to A is isomorphic to A itself. So maybe this is an easier Yoneda exercise if you want to go do it. Yeah, so the last thing I want to say, okay. So this is a concluding remark, but so I guess it's another definition. So what is a compact closed monoidal category? Again, C tensor I. So we know what closed monoidal category means. So if we say compact, it means that if, well, I'm messing up the English, who cares? So if every object in C has a dual. So if every object is dualizable, again, true for finite dimensional vectors. I mean, Yeah, true for finite dimensional vector, true for finite Hilbert spaces, finite dimensional. You can dualize everything in the sense Walker explained in the previous lecture. So yeah, and now there is a nice interplay between duals and the closeness here. I mean, this is the end of the definition. And the general facts you can prove is that if a closed monoidal structure has duals for every object, then really the internal Hom is computed to be just B joule times A, or A joule, B, yeah. You can prove this, and I mean, and an easier thing is to show that the dual coincides with the internal Hom from A to the unit. And if you think of vector spaces, this is, I mean, think of Hilbert spaces, right? So we take Hilbert, the space of linear functionals from a Hilbert space to the complex numbers gives you the dual. And this is true now for any compact closed monoidal category.
Oh, I think you need to fix the first one. If you said P is equal to Y,
Yeah, A dual, yeah, sorry. So yes, thanks. So these things are sort of deducible by general abstract category theory. Again, Yoneda lemma and that kind of stuff.
did you talk about duals in the previous lecture?
Yes, Walker.
Spent like the last half hour of the doing string diagrammatics.
Oh, I see. Okay. Yeah.
Dual is like, well, one sense of it. If you want, let me briefly explain perhaps the sense of this so that we do I have two minutes or it's done?
I mean, it's done, but I don't object to taking 2 more minutes.
Uh,
I think it's really nice.
yeah, okay, so let's do it here. Okay, so suppose that I'm looking at, suppose I want to show that, let me find my notation here. Okay, so suppose I have a map from A to here. Okay, just take a map. Okay, now using what's a dual really? It's just sort of the inverse of the object in the monoidal structures. You can think about it simply like that. So I can just multiply this by B. So let's say I have this F. I can do then, just let me write straight A tensor B because things are symmetric. So I multiply this by B.
So a compact closed monoidal category is implicitly symmetric?
Yeah, I should say symmetric, I guess. Yeah. Yeah.
I mean, you can define compact closed more generally, but every example.
Yeah, symmetry is sort of assumed in any. Yeah, I apologize for not. And so this is sort of, now we have an isomorphism to the unit, which makes this whole thing just isomorphic to C. So really, it's saying that maps A tensor B to C are the same as maps from A to B dual times C. Okay? You can go like back and forth. And now it's just saying that this B dual tensor C, I mean, is this satisfies the same property as the internal Hom. And the internal Hom is supposed to play this role. And so these Yoneda arguments, which we haven't really defined, sort of say that if two objects satisfy the same universal property, they have to be isomorphic.
I mean,
So
one thing to be careful of is that the tensor of B and B dual is not usually isomorphic. It has its canonical unit and co-unit.
yeah, okay, sorry.
These do the right things on Hom sets.
Yeah, okay, so you can go from here to here, but then you can go back with the co-unit, and that gives you the byte. Yeah, I'm sorry. Yes, okay. Yes, thank you. Yeah, so.
Sorry, when you said thank you, I thought you were. When you said thank you, I thought that was a summation.
No, I thanked you for. Okay.
Are there any questions? Sorry, which is the inner product of the Hilbert space of maps between two Hilbert spaces?
So we were computing that in the office. If you take you can use the joule to figure that out. Like, so you want to know.
This formula he just gave, since we've already given
Yeah.
formulas for the tensor product on, or for the inner product on the tensor product and the inner product on the dual, you can just combine those together.
Yeah, I mean, this is sort of isomorphic to this. So to figure out but I mean, well, I did this step unintentional, but it's just this, right? So look up the formula for inner product on the dual and the formula for the, I mean, it's just pointwise on the tensor, and translate it back to what it means here, and you can write down a formula.
I think it would be nice to do it in brackets. I think that's.
Yeah.
It's also worth pointing out that since the dual is not unique, but rather unique isomorphism, a choice of a dual involves a choice of bases. Similarly, you can make a choice that's unique up to unique isomorphism of your internal Hom.
Yeah, that's why also in the dagger structure, like, okay, for matrices it's uniquely defined, but depends on the choice of bases. And so, yeah, there are those choices involved. But pretty much, I mean, if you're interested in a computational basis in the first place.
So this assumption of finite dimensional Hilbert spaces.
Of course, yeah. Otherwise,
Dual objects.
yeah, dagger doesn't exist. Duals don't exist. Like, without finite dimensionality, all this flies.
I mean, actually, this is also a fun exercise because it uses computational categorical. A vector space has a dual if and only if it is finite.
You can, yeah, okay, that's a fact.